Hi everybody, welcome to this video on continuous functions. We're going to explain what a continuous function is in this video. We're going to start with a description that's less mathematical and show some examples. Next we'll show a connection between the limit of a function at a point and the continuity of the function at that point. We'll then cover the definition of a continuous function. We can think of a continuous function as one that we could draw with a pen on a page with an unbroken line without lifting our pen from the page. Here we have an example of a continuous function. We have the function y is equal to 1 defined and plotted here on the closed interval from 0 to 10. This is a function which we could draw with an unbroken line without lifting our pen from the page. This is also a continuous function. Here we have y is equal to f of x is equal to x squared. And this function is defined and plotted on the closed interval from 0 to 6. This is also a function which we could draw with an unbroken line. This is also a continuous function. This is the function f of x is equal to sine x. It's defined and plotted here on the closed interval from 0 to 4 pi. And this is a function which we could draw with an unbroken line without lifting our pen from the page. Having seen these examples of continuous functions, now we're going to talk about when a function is not continuous. We're going to talk about discontinuity. If a function is not continuous at a point, we say that the function is discontinuous at that point. And we call that point a point of discontinuity. Here we have the function y is equal to f of x is equal to 1 when x is not equal to 6, and f of x is equal to 2 when x is equal to 6. If we look closer at our function here, we can see that this is a function which we could not draw with an unbroken line without lifting our pen from the page. At the point where x is equal to 6, the value of our function is equal to 2. But at either side of that point, the value of our function is equal to 1. At the point where x is equal to 6, we have a point of discontinuity. Now, this is a particular type of discontinuity referred to as a removable discontinuity. We could remove the discontinuity if we set the function value at x is equal to 6 to be equal to 1. Here on this screen is another type of discontinuity referred to as a jump discontinuity. Here we have the function y is equal to f of x is equal to 1 when x is less than or equal to 4, and f of x is equal to 2 when x is greater than 4. And this function is defined and plotted on the closed interval from 0 to 10. At the point where x is equal to 4, there is the jump discontinuity. The value of our function immediately after x is equal to 4 is equal to 2. We could not draw this function with an unbroken line. Now we're going to talk about defining a continuous function. To give the mathematical definition of a continuous function, we're going to use some more formal terms. Some of the material we discuss will be both approaching and at undergraduate university level. This is a diagram of a closed interval, with the interval highlighted in green. The points A and B are the endpoints of the interval, and all of the points between A and B are interior points. A closed interval from A to B is all of the points between A and B, as well as the points A and B. We write the closed interval from a to b as open square bracket a, comma b, close square bracket, or as a is less than or equal to x, x is less than or equal to b. Intervals are often used to define the domain and range of a function. The domain of a function is the set of allowed inputs to the function. The range of a function is the set of possible outputs from that function. If we look at our plot on the right hand side of the screen, here we have a plot of y is equal to f of x is equal to x squared. For this example, with f of x is equal to x squared, we define the domain of the function to be the closed interval from 0 to 6. In other words, the allowed inputs to the function are values of x from 0 to 6. And for this domain, the range of the function, or the set of possible outputs from that function, will be the closed interval from 0 to 36. We're going to talk a bit more about interior points and endpoints now. If we look at our function here at the bottom right of the screen, here we have our function again. The function f of x is equal to 1, where x is not equal to 6, and f of x is equal to 2 when x is equal to 6. If we define the domain of our function f of x to be the closed interval from 0 to 10, shown here on our plot, the interior points are the function points between x is equal to 0 and x is equal to 10 for this function. And the endpoints for this function are the function points at x is equal to 0 and x is equal to 10. Now we're going to introduce a connection between continuity and limits. We can think of the limit of a function f of x as x approaches some value c as the value that the function approaches as x approaches c. Shown here at the bottom right of the screen, here we have our plot f of x is equal to 1 when x is not equal to 6, and f of x is equal to 2 when x is equal to 6. If we look at a particular point on this plot, highlighted with this red circle, the point where x is equal to 4 and our function value is equal to 1. We can refer to that function value at x is equal to 4 as f of 4, and that's equal to 1. At this point highlighted with this red circle, the limit as x approaches 4 of our function f of x, that's equal to 1. So as the value of x gets closer and closer to 4, our function f of x approaches the value 1. So the limit as x approaches 4 of f of x is equal to the function value at that point, f of 4. The important idea to note here is that the limit of the function at that point is equal to the function value at that point. And we'll see why this is important now. This brings us to our first definition for continuity at an interior point. A function f of x is continuous at an interior point c of its domain if the limit as x approaches c of the function f of x is equal to the function value at that point, f of c. If we look at our plot, and in particular that point highlighted in red, our function value at x is equal to 4, which we can describe as f of 4, that's equal to 1. And the limit as x approaches 4 of our function f of x, that's also equal to 1. So our limit as x approaches 4 of f of x, it's equal to the function value at that point, f of 4. So by our definition at the top of the screen, f of x is continuous at the point where x is equal to 4. If we now look at a different point on our plot, if we look at the point now highlighted with this red circle, the point where x is equal to 6 and our function value is equal to 2. Our function value, f of 6, that's equal to 2. But our limit, as x approaches 6 of our function f of x, that's equal to 1. As our value of x gets closer and closer to the value 6, our function f of x approaches the value 1. So our limit, as x approaches 6 of f of x, does not equal the function value at that point, f of 6. So by our definition at the top of the screen, f of x is not continuous at the point where x is equal to 6. So we've just talked about continuity at interior points. Now we're going to talk about continuity at an endpoint of a function. A function f of x is continuous at a left endpoint a of its domain if the limit as x approaches a of f of x, the one-sided limit, is equal to the function value at that point, f of a. And a function f of x is continuous at a right endpoint b of its domain if the one-sided limit as x approaches b of the function f of x is equal to the function value at that point, f of b. So there are some terms here which may potentially be new if you haven't seen them before. So we're going to spend a bit of time to explain this. And we're going to do that using this plot on the right hand side of the screen. Here we have the plot of the function y is equal to f of x is equal to 1 when x is not equal to 10, and f of x is equal to 2 at the point where x is equal to 10. And this function is defined and plotted on the closed interval from 0 to 10. If we look at the point where x is equal to 0 and y is equal to 1. So this is the left endpoint a of the domain of our function, the point where x is equal to 0. So a is equal to 0. Our function value f of a, that's f of 0, which is equal to 1. The limit at x is equal to 0, that's a one-sided limit. That limit as x approaches a of f of x, that's a one-sided limit and a particular type referred to as a right-hand limit. It's the value as x approaches a from the positive side, the value of our function f of x as x approaches a from the positive side. For our function to be continuous at that left endpoint a, then the one-sided limit, the right-hand limit, the limit as x approaches a from the positive side of f of x, that has to equal the function value at that point, at that left endpoint a, f of a. Now the right-hand limit as x approaches a of f of x at x is equal to 0, the value that our function approaches is equal to 1. And our function value at that point, at x is equal to 0, that's also equal to 1. So our function here is continuous at its left endpoint, x is equal to 0. If we now look at a different point of this plot, if we look at the point where x is equal to 10, this is the right endpoint b of our function. So b is equal to 10, x is equal to 10 at that right endpoint. The one-sided limit as x approaches b from the negative side of f of x, that's a particular type of one-sided limit referred to as a left-hand limit. It's the limit as x approaches b from the negative side of our function f of x. It's the value that our function approaches as x approaches 10 from the negative side. And the value that our function approaches is 1. But our function value at x is equal to 10 is equal to 2. F of 10 is equal to 2. So at our right endpoint, where x is equal to 10, our one-sided limit at that point does not equal our function value at that point. So this function is not continuous at its right endpoint, x is equal to 10. Now that we have definitions for continuity at interior points and endpoints, we can now define continuity at a point. A function f of x is continuous at an interior point c of its domain if the limit as x approaches c of f of x is equal to the function value at that point, f of c. And a function f of x is continuous at a left endpoint a of its domain if the right-hand limit as x approaches a of f of x is equal to f of a. And a function f of x is continuous at a right endpoint b of its domain if the left-hand limit as x approaches b of f of x is equal to f of b. So now that we have our definition of continuity at a point, we can now answer our question, what's a continuous function? A continuous function is one that is continuous at every point of its domain. Here for this function f of x is equal to x squared, this function is continuous at every point of the domain used here from 0 to 6. So this is a continuous function on this domain. For this function, y is equal to 1 on the domain from 0 to 10, it is continuous at every point of its domain. We can describe it as a continuous function. For this function, f of x is equal to sine x on the domain from 0 to 4 pi. It is continuous at every point of its domain, and we can describe it as a continuous function. For this function, where f of x is equal to 1, where x is not equal to 6, and f of x is equal to 2, when x is equal to 6. This function here has the domain from 0 to 10. And there is a point of discontinuity at x is equal to 6 for this function. So this function is not continuous at every point of its domain. So we cannot describe this function as a continuous function on this domain. But there is an important distinction here. We can describe a function as being continuous on an interval if and only if it's continuous at every point of the interval. If we do not include x is equal to 6 on the interval, then we can describe the function y f of x is equal to 1 where x is not equal to 6, f of x is equal to 2 when x is equal to 6. We can describe it as continuous on a subinterval. From x is equal to 0 to x is equal to 5, this function is continuous on that interval. And from x is equal to 7 to x is equal to 10, this function is continuous on that interval. But it is not continuous at every point of its domain. So we cannot describe it as a continuous function. We're now going to talk about the intermediate value property. A function that is continuous on an interval has the intermediate value property on that interval. This means that if the function takes on two values, it also takes on all the values in between. Here we have our function f of x is equal to sine x, defined and plotted on the closed interval from 0 to 4 pi. On this interval, the function takes on the values 1 and minus 1. And this function is a continuous function. It has the intermediate value property. And because it has that property, it also takes on all the values between 1 and -1. Later we'll use the intermediate value property to prove an important theorem. I'm going to end this video with some examples of other types of discontinuities which you may encounter. Here on this plot we have the function y is equal to f of x is equal to 1 over x. If we look at the point where x is equal to 0, at x is equal to 0, our function is undefined because we have f of x is equal to 1 divided by 0. So our function value at x is equal to 0, that is undefined at that point. But our one-sided limit at x is equal to 0, our right-hand limit, that approaches infinity. So by our definition for continuity at an endpoint, we have a point of discontinuity at x is equal to 0. And this is a particular type of discontinuity referred to as an infinite discontinuity. This is an example of another type of discontinuity referred to as an oscillating discontinuity. Here we have the function y is equal to f of x is equal to sine 1 over x. If we look at the point where x is equal to 0, the right-hand limit as x approaches 0 of our function f of x does not exist, because as our value of x gets closer and closer to 0 from the positive side, our function value oscillates at an ever-increasing rate. It doesn't converge on any one particular value. So our right-hand limit at x is equal to 0 does not exist. So at our endpoint of our function where x is equal to 0, we have a point of discontinuity. And this type of discontinuity, it's referred to as an oscillating discontinuity. So to summarize, in this video we've defined a continuous function. We provided examples of functions that are continuous and examples of functions that are not continuous. We've also described the intermediate value property of continuous functions. If you found this content useful, please subscribe to the channel to receive more content. Thank you very much for your time, and see you next video.